So I just wanted to start off with a quick demo. Live demos are always a little bit fraught, but we have done this for visitors to the Breakthrough Listen Lab. We've done it in sort of hands-on tutorials. It's a little bit complicated this year. Obviously, most of you have the RTL SDR devices sort of on hand, but we haven't been able to kind of sit down and actually sort of work you through tutorials with those, and it's even more challenging given that there's sort of a range of different operating systems that people have, and it's sort of difficult to have you know, a single sort of set of instructions given that there's so many different ways of doing things on different OSs. But I did just want to demo again sort of a similar demo to the kind of stuff that we've done with visitors to the Breakthrough Listen Lab, just to kind of illustrate how SETI works. I think this is a nice kind of visual, and also to illustrate waterfall plots and to illustrate some of the software that can be used to interface with the RTL SDR. So, you know, probably most of you have now one of these little USB sticks and a little antenna plugged in. So I have a little antenna here. I actually have two RTL SDRs plugged into my laptop right now for reasons that will become clear. And I have a nice big discone antenna that's sitting here as well. Just kind of sticking out or sitting in my window here. So I'm going to share screen. And hopefully you'll be able to see the details here. So on the left here, I have the GQRX window open, so you can install this if you're on a Mac with Mac ports. There are sort of similar GUIs basically that you can use on Windows or on Linux. If you have Mac ports, you can just do a sudo port install GQRX, and it'll take a while to compile, but then you should get this program that you can run from the command line. And hopefully you're going to hear the sound here. Actually, I wonder if it's going to funnel the sound to Zoom from the sound card. I'm not sure whether I have to go to preferences on Zoom for this. Some audio settings window, which is opened who knows where on some desktop somewhere. I guess I'll just try and let me know if you can hear this or not. So one of the most powerful transmitters in the Bay Area is our local public radio station, or in the FM band anyway, KQED. At least sort of from where I'm sitting, we can pick this up nice and clearly at 88.5 megahertz. So I'm going to just start this. You hear that?
Results that we're seeing today, which are some stabilizations.
So you're seeing here the basically instantaneous spectrum here that's coming from this FM radio station, and then you see the waterfall plot scrolling down here. I'm going to actually sort of turn the volume down on this a little bit here just by turning the gain down, and you'll hear that's actually dropped below the level at which I have this squelch setting here, basically, which is sort of a cutoff below which you're not going to hear the sound. So if I move this off here, I guess if I turn the gain up, you hear a bunch of white noise here. And then if I turn it down, basically the squelch is so that you don't have to listen to a bunch of white noise if you're not actually on the signal that you're interested in. But you can move the tuner around here and pull it over to the thing that you're interested in listening to. You can turn the gain up a little bit.
But what models are you looking at in terms of?
And so, you know, there's a couple of kind of key things that you can see here. One, sort of instantaneously, again, you have the spectrum at the top, which is just sort of over some small interval in time. Basically, the power that's coming in is a function of frequency. Scrolling down here, the waterfall plots are the same data, and you can see why, you know, we refer to these as waterfall plots, because it looks like water coming over a waterfall, where the water that came over most recently is up at the top, and then it's flowing down towards the bottom here. And this is the FM signal. And I like this visual because you can see basically, you know, on the horizontal axis here, we have frequency going from about 88.1 up to about 89 megahertz. And then on the horizontal axis scrolling down is time. And you can see FM stands for frequency modulation, right? So what are we modulating here? What are we actually kind of using to encode the signal? We're modulating the frequencies here, and you can see it almost sort of looks like a little voice print. Like, you might, if somebody said to you, like, draw what somebody's voice looks like, you might sort of draw something like this kind of wave sort of shape here. It's not really a wave, right? It's a wave that's encoded, encoding the audio information by modulating the frequencies of the signal here. And then the other thing that's kind of interesting, you see on the side here, these two bands that are scrolling down here that look sort of sharp-edged, right? That's the digital information that's associated with this FM station. So if you have a radio maybe in your car, and you have sort of maybe not a very high quality FM signal, but then on certain stations you see a little light up on your radio. It says HD radio, and suddenly you're getting something that sounds closer to CD quality, because it's actually encoding the information digitally, which is more sort of resistant to interference, basically, in the digital signal. And you can also sort of pack more information into that digital signal more reliably than you could do with an FM signal. So if I turn the gain up here again,
conversations really happening in our.
So I'm using this FM decoder right now, but if I scroll this over to the digital signal just sounds like noise, basically, when I'm decoding this with an FM decoder. It's the wrong decoder to use to demodulate this thing, right? I actually need to have be able to unpack the digital information that's in here in order to get that signal back out. But it's also sort of an example, you hear noise here, you hear noise here when I'm on the signal. This noise is a little bit louder when I'm on this signal than here. And again, I come back onto the FM signal and I can understand this.
Speed up testing, and what's the problem?
But you can see even this digital signal where I don't have my sort of decoding set right, I can still see that there is information there. And even though it looks noise-like, right, there's this Nyquist theorem, which basically tells you there's some sort of fundamental limit in terms of how much information you can pack into a certain bandwidth. And if you pack sort of the maximum amount of information in there, then it will start to look very close to noise, basically. It's sort of the entropy of the signal is going up. But even though there's a lot of information packed in there, and even though I'm not decoding it, I can also see these sharp edges, which obviously look artificial. And so this is, not as narrow band as some of the signals that we're searching for in SETI. These signals are, a few, I guess, tens of kilohertz wide here. But as opposed to the few hertz signals that we're looking for in SETI searches, but they still obviously look artificial in this waterfall plot. There's obviously kind of information in here. So the other thing that I can do is, I can say, well, let's tune to a different station. I can type that in here. Again, I'll sort of turn my gain up again. And now we're listening to music, right? FM music, and you can see the signal looks pretty different here to the voice that we were hearing from the public radio station here. Still looks like FM, but it's sort of qualitatively different when you look at this. And I can tune to, there's some other FM stations here. So if you're tuning your radios sort of up through the band, this one's kind of right at the edge here, but more, another sort of talk radio station, again, back to the music station here again. The other thing that I like in the Bay Area, we can also pick up signals where they're still FM, but anybody speak Spanish? I don't, so I have no idea what they're saying here. Here's another one. No, I'm not picking that up. I guess I had a better, another antenna here. Let me see if I can. Again, a problem with live demos here. I guess we're not going to get that one. I'm going to go back to the Spanish language station. This one was a Chinese language radio station. I'm going to go back to 98.9. So again, even though I don't know what is being said here, I can tell that something is being said. And this is sort of what I like about this as a SETI analogy, right? Even if I can't decode it, So even if I know what the modulation is, right, there's a language, but then there's sort of a modulation scheme that's being used. But even though I can't decode this, I can tell that there's some information there. I can tell that it's an artificial signal. I can tell that there's some intent, which is kind of a fun sort of way of thinking about this. We can also go to much higher frequencies with these things. So you can look some of these frequencies up on the internet, but I'm going to try this. And I'm going to go to narrowband FM signal. And again, these live demos are a little fraught. Let me just play around with the script a little bit here. We don't have to listen to all that noise. No, here we go. So you can see there's a bunch of signals here that are scrolling down. We'll try and kind of catch one of these as they come through. See if that comes back. So that's the Bay Area Rapid Transit system, and they have narrowband FM radio. So the drivers are talking to the BART control center and reporting.
Train 509, you wanted me to come in on platform 2 for daily tip. That's where the schedule takes you.
Maybe not super exciting to listen to what platform the Daly City train is coming in on, but it is kind of cool that you can also sort of pick this up again, sort of using this little $20 device.
And Steve, you knew that this was the right frequency for, I guess.
Yeah, I mean, I looked this up, and you can see, you know, there's a whole bunch more signals that are packed in here. So there's different drivers that are turning their radios on and off at different times. There's also a system called trunked radio, which basically kind of allocates open frequencies on the fly, basically. So they're kind of jumping around, and you won't always hear both sides of the conversation. Some of these radio transmissions are also encrypted. I mean, you know, you can listen to police scanners and that kind of thing, but you know, there's also some of this where you're not going to be able to listen in for one reason or another. But yeah, there's a bunch of these frequencies online that you can go and look up and then you know, just sort of scan around and see what's out there.
What does an encrypted one sound like?
It sounds like noise because you're not decrypting it properly, basically. I mean, it's you know, and there's data. I mean, this looks like data here, so probably if I turn that up, it's going to sound horrible. So I don't know what they're transmitting there, but you know, again, you can sort of poke around and see what's out there. We can also do AM. So AM radio frequencies, typically broadcast radio, are lower, much lower frequencies, but there's some AM transmissions that are used by aircraft, and we can try tuning into some of those. So I can go to 20.9. Catch these, some of them are kind of coming and going pretty quick. So. Actually, I guess I'm not getting the signal at all. Really. That's loud. Sorry about that. Oh, so this is working away. Well, we can come back to this. I'm going to try another frequency here. And there's a couple of frequencies commonly that are used for car keys. One of them is 315. I happen to know that my truck key here is at 315. It's a little loud. My truck's sitting in the driveway, so hopefully the neighbors aren't hearing the thing going on and off, but you can see when I press the button here, I'm getting a little transmission here. And again, I like this because like we're not listening to voice here. We're not even listening, like we don't even know what the encoding is. I mean, you know, Derek could probably say more about like how these things are working and how they're sort of cycling through the different codes that mean that when I click this, I'm not unlocking somebody else's vehicle. You know? But the thing that I like about this is we can use this as a little demo, you know, from a SETI perspective. Okay, so, you know, you don't speak English on the other end, you don't speak Spanish, you don't speak Chinese, you don't speak any human language, you don't understand FM, you know, we have no sort of prior agreement about how we're going to communicate with each other. So there's this idea that we talked about a little bit about Schelling points, right? It's this idea that, well, you know, where shall we meet if we have no prior information? You know, maybe we should meet at, you know, if we're in New York and I say, okay, I'm going to meet you in New York and that's all you know, you're probably going to meet me at noon rather than at, you know, 3:22 p.m. You're probably going to meet me at Grand Central Station rather than at the corner of, you know, 57th and Madison Avenue or something, right? There are certain points where we can sort of say, okay, this is a good place to look, or this is a good sort of transmission scheme to use, knowing that the person on the other end doesn't have any prior information about, you know, how we're going to do this communication. So, you know, how might we do this from a SETI perspective? Well, again, here's my car key. Okay, so everyone can count, right? Even hopefully ET can count. So 1, 2, 3, 4, 5. You know, this is also kind of not necessarily even requiring us to use the same numbering system, but you could recognize these pulses as being something that has some intent behind them. I mean, a single pulse like that, you might say, oh, I don't know, maybe that's a fast radio burst or something. But if the fast radio burst shows you that it can count, or shows you that it can do math, or, you know, has some other information that's packed in there that you can get out, then that's pretty interesting. And I think sort of one thing that this also kind of illustrates to me from a SETI perspective is that, you know, we're looking for these narrowband signals. Glad Rachel and Fatima are on here because they're, you know, some of the folks on our team who are thinking about kind of non-narrowband signals and thinking about other algorithms that might look for sort of a broader range of potential signals in the data. You know, a narrowband search algorithm, a Doppler drifting narrowband search algorithm would miss the information in a signal like that, even though it's obviously, right, 1, 2, 3, it's an anomaly. It would look like nothing else in the data set. So, you know, we want to do a broader search to find stuff like that. I'm going to just try, see again if I can go down to the aviation frequencies again. I guess we just missed somebody there.
Wait, Steve, why would narrowband search miss your car key? Isn't it producing a narrowband frequency?
Well, that was broad in frequency, but short in time. It was more of a kind of like a pulse search might find it. So, you know, some of the stuff like the Spandak pipeline that Vishal has been doing might find a pulse like that, but then it might miss the fact that the pulses are doing something weird, right? Again, we're not sort of looking for somebody being able to count, for example. I mean, you know, this is sort of a little bit contrived, right? And Derek's going to lead us through the Voyager tutorial, actually detecting Voyager in GNU Radio. And you know, you, Alon, have been working with detecting Voyager using, you know, doing a narrowband search the same as we do our standard narrowband search, and that was the thing that came out, right? You found Voyager in the data, so I'm not saying it's hopeless. You know, we should still do the narrowband search. It's really great at finding stuff like that, but there may be some other stuff that we miss because you know, it's an anomaly, but it's not sort of an anomaly where that narrowband search is sort of tuned to detect it.
Got it. Okay. It just looks like right now it's there's some narrowband signal, and that's what I was confused.
Oh, here now, yes. And now I've tuned back down to lower frequencies. And I think actually what we're seeing here, I think, is just the DC spike in the hang on. I missed that. Well, you get the point. So what I was going to try and do was to run GPRX simultaneously with the other SDR that I've got plugged in here, because there's also this code called dump 1090, and this is the bit that I couldn't get running here. I couldn't get the web. Let's see, maybe we'll have some of this. So dump 1090. Okay, so you're hearing something that sounds like the communication with it. Sometimes you can actually hear. Sometimes you can hear the call signs coming over here, and then the nice thing is as well, right, that it tends out. Sound there for a second. Okay, that's better. So simultaneously with the voice communications with the tower, also at 1090 megahertz, planes are transmitting their basically position information, their velocity, their altitude, all of this kind of information. You can just pick that up. So I've got 2 antennas and 2 SDRs here, so I can run this simultaneously. And you can see it's already picking up at least one plane there, and as you kind of let it run, it's going to pick up some more. So this one, we're actually not getting an ID from that first one other than this kind of hex code, but it's its altitude, 9275 feet, I guess, speed 296 knots, heading 20 degrees. And then, for some of these, you'll start seeing, a Southwest flight or, a United flight or whatever. And then you'll actually see their flight number come up here, and maybe also their transponder code under the squawk column here. And then you might get latitude and longitude out of some of these as well. So what should work here and wasn't when I tried this before, and I'm just going to try this one more time, is actually there's the interactive, or I guess interactive means it's updating. There's also an option that you can supply that should plot this up on a web page, and this wasn't working when and now it's not working, and I'm not sure why I had this working before, but you might be able to get this sorted. And so it'll actually plot a Google map with the plane positions on the Google map, and then you can click on them and you can get the information that you can also get out of this table here by clicking on those planes. It works better if you go and sit outside, and particularly if you just have a small antenna and you're outside your house kind of watching planes going over. You can see which plane it is, you can plot it up on the map, you can get the transponder information. So this one we're getting latitude and longitude now, and it's Southwest flight 1892. So maybe we can also hear them over the radio. Let's see if we can pick them up. And again, there's a bunch of different. Sorry, blasting people's eardrums there.
This is so cool.
So there's a bunch of frequencies that you can use for communicating with the tower. Here's a private plane, right? This N number means that's the tail number on the plane, N534 PD. So you could maybe, you can also look this up. You can look up the tail number and probably find a picture of this plane somewhere online. So there's a bunch of aviation frequencies. So we're listening to NorCal departures here, I think, but there's also Oakland Tower, San Francisco Tower, San Francisco ground, and you can hear all of these communications taking place on the different frequencies, but obviously kind of not all at the same time. So you need to be sort of listening to the right.
How far away can it detect airplanes?
So that was Southwest something. I don't think that was Southwest. Southwest 2176. So we'll see it. Southwest.
2176, reading 3,000 direct to Ross. 73,000 direct to Ross, Southwest 2176.
Southwest 2176. Maybe we'll keep an eye out for that popping up on here, because obviously they're talking to NorCal right now. How far can you detect it? I mean, it depends sort of, whether you have my antenna is just sort of sitting in a window here. It kind of depends on a bunch of other things, like line of sight, or the gain that you have, the antenna, the SDR that you're using, and that kind of thing. But I guess sort of in practice, I can certainly see planes. I'm here in Oakland. I can see them kind of out above the Oakland Hills and sort of out over the bay, but not so much kind of as far as SFO itself, or kind of over the hills. But you could play around with this and see.
And sorry, Steve, did you say this is like a special edition? Like how did you load this plane detection?
Dump 1090, there's a GitHub repository, and you check that out, and then there's instructions about compiling it. So it's not kind of click and install software. This is unfortunately not something that's going to run on a Chromebook in your classroom, but you can download it on a Linux machine or on a Mac, and compile it, and it should run. That we consider help troubleshoot as well, but it doesn't. I just think it's pretty cool, and it should be kind of more easily installable and widely available, I guess, would be nice. The other thing that you can do if you have one of these and you're picking up this ADS-B is the sort of standard here for transmitting this information. You can actually feed it into, there's a few sites, one of them's called FlightAware, and you can go and look up flight information on the site. So you can, like if a friend or family member is traveling and you're wondering where their flight is, you can go and look it up, and it'll plot it on the map. And one of their data sources is actually people around the country who have this software running, well, not this exact software, but software that is doing this ADS-B decoding and feeding it, over the internet then to their servers, so that they can kind of crowdsource basically the information about the plane. So some people are running them on little Raspberry Pi boxes and just kind of leaving them running all the time, and feeding this in. If you go to their website, they'll sort of tell you where they have regions where they need more coverage. I don't think the Bay Area is really one of them. I think there's a lot of kind of nerds here who are doing this already, but there's probably sort of other parts of the country or the world where they could kind of use people's help. Southwest 2176, there we go, there he is, 7,700 feet, 295. So that was who we just heard talking to NorCal on the radio. So you can't do this unless you've got two SDRs running.
I just went to FlightAware, and it looks like 2176 is an Oakland to Houston flight.
Okay. Yeah, and if you can do that with this, with dump 1090 as well. If I could get the Google map working, you can click on it, and then it says, okay, now go look this up, on FlightAware or whatever, and you get the full track information and everything else. And so what FlightAware actually give you, if you are one of their sort of data sources, they'll give you, and I haven't done this, and maybe I should, it might kind of be fun, but they'll give you like a premium subscription for free, basically, to their data sources in exchange for you helping them out. So yeah, still climbing, 10,000 feet. Cool. So that was really sort of what I wanted to show you. And I guess, so the other point that I wanted to make, right, is that, we're listening to audio information, and we're simultaneously getting digital data over two completely different radio frequencies that are sort of, factor of 10 different to each other. So, it really illustrates, first of all, kind of the breadth of the radio spectrum and the different uses, but also, I think that it's nice to illustrate, including the car key example, right, that people think, and maybe we're not helping by calling the project Breakthrough Listen, but people think, oh, you're listening to the radio, you're listening for ET. Well, yeah, maybe they're going to send us an audio signal that we can decode, but actually it's sort of breakthrough, look for things in waterfall plots, but that is not quite as catchy. So, I guess there's also, I shouldn't sort of diminish the optical search as well here, and I guess Anna's job is a little bit easier than the rest of us, because you see something weird in an optical spectrum, and it's a lot less kind of crowded with artificial signals with radio frequency interference, there are a lot fewer sort of artificial laser transmissions that you're picking up. So that's a point that we shouldn't underemphasize. Any questions or other comments about any of this? And I should acknowledge that there are people on this call who are far more experts in GNU Radio than I am. So if I've said anything untoward here, then please correct me. But, okay, then I'm going to stop sharing, and I think if I can hand over to Derek. Derek is going to show us some of the Voyager data in GNU Radio Companion.
Okay, I'll pull that up. One of the exercises that I actually do with some other people within GNU Radio and with another tool is reverse engineering the signal from these little pagers that you get at restaurants that beep and buzz when your order's ready. But of course, I can't find the power supply for the transmitter, so I can't demo that right away. But if anyone's interested, I can probably at least send some notes on that.
So can you trigger other people's pages, and they're sort of running up to get their order, and potentially it's just you behind a bush somewhere?
We used to regularly do this to Matt Edis, who was one of the founders of a company building software-defined radios, and he found it kind of funny the first time. But all right. It's on to Voyager. So the other thing I was trying to do was I was trying to connect to a radio station near where you are, Steve, to see if I could transmit and you could receive. But of course, I don't have that entirely set up either. So, oh well. This is the other thing that I haven't figured out yet. So, okay. So so first of all, so I'm going to go through a couple of slides about receiving Voyager, mostly talking about Voyager as a probe and what makes it such a challenge to receive it. And then we'll step through some pretty simple digital signal processing steps within GNU Radio. I've posted the starting point, so the kind of the template for the GNU Radio flow graph into the Slack channel. So if you can grab that and figure out how to load that into GNU Radio from whatever environment you have. The only one that I imagine might be a little bit tricky is people who have the Windows subsystem for Linux. You just have to make sure that you're able to actually open a Windows file from within it. The other thing that you need is the actual data file that contains the recording made at Green Bank. And that's the one that Steve posted a link to last night. It is 1.3 gigabytes. So if you haven't started downloading that, that's probably not going to finish downloading fast enough now. But we'll kind of walk through it, and that shouldn't make too much of a difference. So share your screen. Every time I try and make this presentation full screen, it ends up being 2 monitors wide, and then I can't see anybody else. So I'm going to leave it in this format. So I have this kind of subtitled, Listening to a Butterfly on the Moon, because the amount of energy that we end up receiving from Voyager and other radio astronomy targets is so small that there's probably, we probably almost get more vibrational energy from a butterfly on the moon than we do from some of the very distant pulsars and stuff like that. But I'm probably not off by that many orders of magnitude. So Voyager 1, it's the farthest ever, it's the farthest human-made object from Earth at this point in time. It was launched 39 years ago, and one of the things I find really interesting about it is it did a bunch of gravity assists within the solar system. So it flew by planetary objects so close that and in the same direction as the planet was orbiting, that it actually got dragged along by the planet for a short amount of time, and that accelerated it. So this is part of how they sped it up to the velocity that it's at right now. And on its final gravity assist, instead of coming around on the same plane as the planet was rotating in, it actually came from close to the bottom and ended up shooting up out of the axis of our solar system. So it kind of took a right turn at the last minute, and it's now headed, not straight away from us. It's headed vertically away from the plane of rotation of the Earth. And so one of the interesting side effect that has is that Voyager 1, over the years, has been kind of spiraling away from the Earth from our point of view, and is now an increasingly stable point in the sky, rather than kind of just flying off in a direction that changes a lot as the Earth rotates around the sun. It's really actually just prescribing a tiny little circle in the sky. An interesting side effect of this, and I'm slightly diverting here, but just interesting facts that I learned. There are 3 main telescopes that are used, radio telescopes that are used for communicating with Voyager, and they're kind of spread about a third of the way around the Earth. And because it flew off in this sort of pattern, Voyager 1 can still be seen by, I believe, all 3 radio telescopes, or radio communications dishes, but Voyager 2, which headed in the opposite direction from the plane, can now only be seen by, I believe, 1 of the radio telescopes, the one that's in Australia, because it's basically in the southern hemisphere of the night sky.
But Derek, if it were the opposite, are you saying that Voyager 1 is not like above the North Pole?
It's not far enough above the North that the southern radio telescope can't reach it.
Got it. Okay.
But yes, it could definitely have had that problem had it made a bit of a sharper turn. And I have not worked out the orbital dynamics or anything near it to figure out what exact angle it's traveling at. Just it was one of those interesting reminders that space is 3-dimensional. And so when we say it's the farthest away, we have to remember that it's traveling along multiple axes. So Voyager 1, I have a photo of it. Actually, I'll flip to that first. So this is one of the Voyager space probes. So we can see the sense of scale relative to a person. And we can see that actually the vast majority of it in terms of mass and size is dedicated to the communications equipment. There's a hunk of plutonium which is powering it just by giving off heat, and that's converted to electricity. And so that radiothermal generator powers all the communication systems as well as the scientific payload. And so this communications dish, which is the high gain antenna, is 3.7 meters wide. So it's less than half of the diameter of the Allen telescope array antennas, for instance, and a lot less than half the surface area. And that's the main link back to the Earth. And it ends up with most of the energy from this antenna is squeezed into a 1/2 degree wide arc headed back towards Earth. So it has to point very exactly towards Earth. And the actual radios that it's broadcasting with are less powerful than like the ones I have on my desk, 20 watts maximum. And that was when it was launched. This equipment is now 39 years old, and so they've actually had to continuously kind of turn down the settings a little bit as equipment aged, failed, as the power supply becomes less powerful because it's decaying as the radiation, as the plutonium decays. It becomes less and less, it has less and less ability to produce electricity. Right now it's at about 75%. And they think they only have about another 5 years worth of it producing enough energy to maintain a link back to Earth. There's 2 main broadcast frequencies. that it uses to communicate with Earth. One is just above 2 gigahertz, and the other is just above 8 gigahertz. These are very standard deep space network satellite communications channels.
Derek, do you know if it's continuously broadcasting like 24/7, or is it broadcasting once in a while?
I believe that it's close to 24/7. I'm not sure how much they're trying to save energy by having it not broadcast. I don't think that it really has any batteries on board, so there's probably not much benefit in it not transmitting. What it does do is Voyager sits and listens for the Earth for the signal from the Earth, and it actually locks onto it. So it will exactly and precisely match its transmitted frequency to a ratio of the received frequency that it's receiving. And this is part of what actually means that we're able to still receive it here on Earth. We know absolutely and precisely what frequency to listen to. If we didn't, it would be much harder to receive the signal and decode data from it. The other thing that's come out of this is that it can send less and less data per second the farther away from Earth that it gets. And this kind of boils down to the simple rule of thumb that you can decode something, you can decode a piece of information if you can receive enough energy about it to tell the difference between like a 1 and a 0. It ends up getting more complicated as you pack the data more and more. But the basic idea is if you don't receive enough energy from that symbol, you won't be able to tell the difference between the different values, and it just ends up scrambled. So what they've done is they can't transmit any louder. The hardware is what it is. And the farther away from Earth it gets, the weaker and weaker that signal is when it gets to us, because it's spreading out. Even though it's focused to a ½ degree, it ends up spreading out quite considerably by the time it reaches Earth. And so they just make it transmit slower and slower. So it spends more time sending each symbol. More time at the same transmit power means more energy in that single symbol. So I checked the NASA website yesterday, and it's currently transmitting about 165 symbols per second. So 165 bits per second. As you can imagine, that means we're not really getting any more photos back from it at any sort of speed. So they have to very carefully choose what data to transmit back from Voyager. And to give, I didn't really have a sense of scale of how far away Voyager is. You know, if I say it's 14 billion miles away from Earth, that number rapidly just becomes somewhat meaningless, at least for me. But to say that it's over 20 light hours away from Earth was at least something that I could kind of grasp. And so, yeah, any command that we send to it takes almost a full day to travel to it, and then another almost full day to travel back.
Yeah, I looked it up. It's like 3.75 times the distance to Pluto.
Okay, yeah. It's 150 times the distance of the Earth to the Sun as well.
And do you know what type of data it is transmitting back? Maybe you're going to get to that.
I know the format of the data, but I don't know the contents of it.
We recorded the raw voltage data last time we looked at it with GBT, so you could take a look at that and see if you can decrypt it.
Mm-hmm.
Dave and I have been trying to work on that. So far, Dave is stumped.
The data file that everyone has downloaded is also actually the raw voltage data. And it what you're looking for, if you did go in and try and very precisely look at the signal, what you'd be looking for is a continuous sine wave, and every now and then its phase would instantaneously flip 180 degrees. And that's what signals a 0 or a 1. So this is called binary phase shift keying. It's using a 39-year-old variant of it, so it's not quite exactly what we canonically call BPSK now, but it's 99% the same idea. So I've largely kind of talked my way through most of these slides now, I think, but the issue is that the signal has gotten tremendously weak. So even when you're receiving with something the size of Green Bank, the signal is right down close to the noise. And unless you're doing some of the advanced signal processing that NASA actually does when they try and receive the data, the best we can hope for, even with a bit of work, is to just see the signals emerge out of the noise. So I think we've kind of already covered this in a few different places throughout the internship, and it may be things you've already seen before, but I was giving these to another group of interns who had a much wider range of backgrounds. So the basic idea of what we're going to try and do is convert this time domain measured signal into a frequency domain, and we're going to try and see the actual Voyager signal as it's transmitted back. We use an operation, and so this converts it into spectral data. So we'll be looking at the amount of energy at a certain frequency, and the Fourier transform allows us to do that. So this is kind of our end target, is to be able to see this. So this is this power spectral density of the Voyager 1 signal from this recording, or from a very, very similar recording. And what we're expecting to see is one very strong signal in the middle, relatively very strong, and that's the carrier signal. That's what NASA is using to lock on to the received signal and say, yes, we're absolutely pointed in the right direction, and we know then that the data should be these two small spikes on either side. So these are the data channels located above and below the main carrier and frequency. So the data set that we have is from the Green Bank telescope. It's 100 meters wide, and so we get a relatively loud version of Voyager, which means it's pretty easy for us to decode, or to at least receive it. It's in a radio quiet zone, so the noise level is fairly low. And because it's such a big dish and they have a very nice feed, we get a very nice receive antenna. We get a good signal. This is something, I'll paste this link into the Slack. We won't go over it today, but this is, there's an IPython notebook that does some of this signals analysis as well. So you can see just a different way of doing a very similar operation that we're going to do in GNU Radio. So the key technique here is we want to do an integration on the data. If we look at just an instantaneous snapshot, what Steve was showing earlier on GQRX, we actually wouldn't see the signal at all. It's so weak, it just looks like noise. What we need to do is we need to add up we need to take a whole bunch of those instantaneous snapshots and add them together. The noise will end up partially canceling out and not consistently having high energy. The Voyager signal, because it's working so slowly and it's at fixed frequencies, has that little bit more energy than the ambient noise. And so if we add it up 100 times, those pieces will come up out of the noise and we'll be able to see those three characteristic spurs. So the basic steps that we need to do are convert the time domain into frequency domain. So we use the Fourier transform for that. The fast version of it is very creatively named the fast Fourier transform, FFT. This will take some number of time domain samples and convert them into energy levels for a bunch of evenly spaced frequencies. So if we took 1,000 samples, ran the FFT on it, or ran a Fourier transform on it, we would see the energy level at 1,000 evenly spaced frequencies. And then the usual operation that we do is square that to display power and convert it into decibels, because we want to see the difference between a large signal and a very small signal displayed on the same graph. If we didn't do this, we'd end up with the noise being almost invisible. And in this case, it wouldn't make much of a difference, but we're going to go through that step anyways, because it is usually how things are displayed, at least in the communications plots.
Derek, are you saying that the dinky little $20, $30 antenna that we use, if you do an integration, can actually detect Voyager?
No, you would need, well, there's a qualifier to that. It is perfectly capable as a radio of receiving Voyager. You would need to like plug it into the Green Bank telescope though. Because if you spent long enough integrating, maybe. But the practical way of doing this is definitely to hook it up to a satellite dish.
Okay.
And there are people who have very successfully received Voyager and have received like transmissions from lunar rovers on Mars. Or sorry, lunar rovers on Mars. Martian rovers on Mars, on the surface of Mars, from their backyards, using those just kind of regular satellite dishes that people used to use for, well, and still do, use for satellite TV. So it's possible to do at home. You need a certain level of enthusiasm.
So you're saying the integration is for the Green Bank telescope?
That's what we're going to do here. Yes.
Got it. Okay, that makes more sense.
There are many signals which you can pull out using an RTL that are stronger signals, but are still below the noise here on Earth that you can pull out. So Ellie, for instance, I know on a past project has used integration to pull out the hydrogen line observation data using an RTL and a relatively small antenna. So it is capable as a receiver.
Yes, sorry, just a quick thing. I've actually not done that, but I work with people who have. And it's really cool what they can do. Pretty amazing.
But you used a horn antenna to receive it.
Right.
Not a little RTL. Or you put an RTL, the horn funneled the signals to the RTL.
Yes. Yeah, it's pretty cool. I've been able to detect like a solar flares, but not H1 yet. I'm working on it.
Cool. Sorry for the confusion there. So this is the actual step that we want. This is what that looks like in GNU Radio. And so I will probably put a screenshot of this into Slack so that you can reference that fairly easily. And yeah, so we can see that this does the steps that I've just described. So it does a Fourier transform on 32,768 samples. This is a convenient power of 2, which works well for computers and not for humans. Then out here at this point, so we've gone from time domain data into spectral domain data, frequency domain data. We square it, which gives us a magnitude value. We want to know how much power is in this signal. And so here we have a power reading. We integrate it by a factor of 100. So it'll take 100 of these measurements and then produce one output. And then we're doing a 10 log 10 operation here. The negative 30 is if you wanted to convert it into dB milliwatts, decibel milliwatts. But given the signal isn't calibrated, that's not really accurate. It'll just be a static change in the number. It won't affect the end plot in appearance-wise. And then we would view the data in the next step here. So that is not, here's what I wanted to pull up. So this is what the file should look like that I I've sent out. So if you're able to open it up, you should see this flow graph here. And what is occurring here is we're reading some data from a file source, doing a bunch of processing on it. And this is stuff that you can read the comments, and I can walk through it at the end if you're interested. But we're basically just doing a bunch, I'm doing some pre-processing of the data to get it into a format that will work well for us. And if I run this, this will show us the single shot, the instantaneous power levels. So this is without any integration. And it also shows us a waterfall plot. And if we look at this with a slightly suspicious nature, we can actually see a line here. You know, and I suppose I should have asked, what do people see here? But hopefully you're seeing that there's more often than not a bit of extra power right at this frequency. And this is Green Bank being a wonderful receiver and actually giving us enough power that on average, you can kind of actually see it in the single shots. But if you were looking at it in this way, you know, you'd never be able to tell.
It also looks like there's a lack of power in that area.
I have no explanation for that. I don't know. That isn't an effect from GNU Radio. So actually, okay, I'm going to take a guess at that. When you receive data using a radio, most of the time there'll be a bit of weakness at the edges. The signal level will drop on the outer edges of the band that you're receiving. One of the operations that I've done is to rotate the spectrum to fix a frequency error. And my guess is actually that this is the two edges have met here and have been rotated a bit. I've basically rotated it kind of around the axis. I bet if I undid those, we would see that these are on either edge of the plot.
It's also possible, Derek, that's the edge of one of the coarse channels. So there's this 3 megahertz scalloping in the Green Bank data that corresponds to the coarse channel width, and that sort of drop in sensitivity there, I would guess, is the boundary between one coarse channel and the other.
So, and that may well be, that may be the answer, and we may only have one channel. And in that case, it probably still would be the band edges. It would just be from a different cause. It wouldn't be the radio, it would be the processing. So I've just unflipped it, unrotated it, and we can see that those weaknesses are, or those power bits are down on the edges.
Yeah, and you're getting about 3 megahertz of band there. So that I think this is sort of one coarse channel extracted from the whole larger file, which would be pretty big. So you only really need the coarse channel in which the Voyager signal is present to do the analysis.
So I've just turned on some heavy averaging. And if we look at this now, we can see that channel fading on the edges. And with this much averaging, we actually can see one portion of the Voyager signal emerging. This is kind of integrating, but not properly. So we'll get a much better signal when we actually integrate. But enough of me showing, time for you to try it out. The only other thing I'll say is you'll have to open up the file source and select this file that you've downloaded. So wherever you've downloaded that to, you'll have to change it. Otherwise, you should be able to just click run and see what I have there. While you're getting that going, I don't know how much more time we have in the session, but while you're getting that going, I'll post a screenshot of the additional blocks that you need to add in here. And when enough people have kind of gotten this first part working, I'll quickly run through adding those blocks so you see exactly how that's done.
And again, we are recording this if folks want to go back and sort of work through things in more detail.
Hey, Derek, I have a question if you don't mind.
Go ahead.
So what's the difference between the averaging that the frequency sync does versus integrating?
Integrating is doing an addition operation on each bin. And so for each frequency index, it's just averaging all of the samples, or 100 of those samples together. The integrating, it's doing a straight addition.
Okay, so basically the frequency sync divides by the number of integrations, or the number of samples in your integration.
Yeah, of course you say that, and there probably is very little difference. Actually, mathematically, why would there be a difference? Yeah, if you're adding, because that's another form of averaging, is if you add 100 together and divide by 100, you'd end up with the average of that set. So yeah, there probably is no difference DSP-wise between them.
Yeah.
I guess the difference, the difference that we'll see in this plot is that the waterfall sync and frequency sync that we were just viewing, we're only doing an FFT size of 1024.
Mm.
And what we'll do in the integration is 32,000. So we get much finer bins, so they'll be less noisy in that way.
Okay.
And I don't know how many integrations the frequency sync was doing there when I turned on high averaging,
Yeah.
but it's probably less than 100.
Okay. Cool. Thanks.
Yeah. No, good, really good point, and one I had not fully thought through.
Appreciate it.
So I figure I'll give it kind of 4 or 5 minutes for people to get the file open, figure out those bits, and then we'll check back around and see how people are doing with that. And then, so that'll be kind of 13, 14 past, and then I'll click and drag the blocks in, and we'll take a look at what the data looks like all together.
Derek, what's the relationship between the screenshot that you shared with us on Slack and the flow chart that you're currently screen sharing?
So the blocks that I shared there, if I change to the completed one, we're going to add those in to process the radio data. So they are the blocks that are missing from the file that I uploaded. What I uploaded should have all of this.
Okay.
A few of us are having errors. Do you have any comments on getting an error about a missing tag and it's a less than sign?
When you draw a connection between blocks, you probably have a curved line or a straight line. You're probably on GNU Radio 3.7. And the file I sent out is for 3.8. I was wondering if that was going to be an issue. Unfortunately, there's no easy way for me to save this file in an older format. All of the blocks exist, so you can drag and drop them in. I'll post a screenshot of this, although, yeah, I mean, that's going to be a little bit painful to figure out some of these values, because like this is 1/127, but that's not obvious just by looking at a screenshot of this. How many, well, I don't know a good, actually you can raise your hands in Slack if I can remember where to see that. If you're having, actually, can you just go, can everybody go under help about, and if the version number is 3.7 or anything other than 3.8, can you just raise your hand in Slack so I get an idea of how many people that's affecting? And that's interesting. I don't think that's used. So I'm just trying to simplify this down in case people are recreating it. Okay. So I see the people who have the 3.7 issue. I will upload a copy of this compatible with 3.7, so you can check it out after the session. It's not too difficult for me to just copy over values. So if we take a look at this, what we want to do is after this processing, we want to do the integration step. And so I'm going to go into the interns channel and pull up that image that I posted. And what we want to do is replace this null sync, which is just dropping data on the floor. We want to start building this flow graph out. And so I'm going to use this as a chance to kind of go over GNU Radio again. You can search for blocks in this tree by name, and you can actually see we have some ATA blocks in this as well. You won't have those on your copy, but it's something that is being put together. And the first piece that we want to put in is the FFT. So it's under Fourier analysis. We can click and drag this in. And we just want to, you can either click and drag, or you can click on the output, click on the input. Either one works. We have this variable which defines the FFT size, and we're just going to reuse that in each of these. So kind of straightforwardly, where it says FFT size here, we just type in the new value. And if you hit, see, I just hit apply, and the arrow went black. So actually, sorry, and we have to change this value here as well. Not to that. So we just update the two values to be FFT size here. And this will take, kind of just to repeat again, this will take the time domain data of this one about 3 megahertz wide channel, and it'll turn it into 32,000 evenly spaced frequency bins. My preview of myself is frozen. Can people still hear and see my screen?
Yes.
Okay, then I will ignore my frozen expression of bewilderment and continue on. I remember this. So that's somebody else's version of it. So then we need to convert the data type. We need to do the magnitude squared operation. And this is just taking every element in the output of the Fourier transform and squaring it. This needs to know that it should work on block sizes of 32,000 samples. So we update the vector length to be FFT size, and it's happy. If you have really good eyesight, you can see the port color change from light blue to dark blue. And if we go under help types, actually it doesn't say from here, but basically we're going from the complex 32-bit number to a vector of it. Then we want to integrate. Great.
When you say a vector of it, you mean integer 32?
So it's we have these 32. The FFT works on blocks of data. In this case, it's working on 32,000 individual samples of data, and GNU Radio wants to know that that block is now going to be passed around as a single discrete object. So it's a single array of data or a vector. And you can imagine that if we had a couple of these output all at once, and we accidentally grabbed like half of one and half of the next one, we would basically be mixing up the results. And that could either look like a frequency shift or well, it would look like a frequency shift of some sort. So we're just telling it, make sure to keep these 32,000 values altogether.
Right. When you went to the help menu to show the data types, it looked like dark blue was integer 32 and light blue was.
Yeah. So the kind of teal, it's probably pretty subtle coming across Zoom, but the teal color is a float 32.
Float 64.
And the complex float 32 is, oh yeah, the float 64 is kind of teal, and the complex, so the IQ values of floating point numbers are a darker blue. It goes even darker when you make it a vector, which is maybe a statement about the usability of this in terms of user friendliness. Now, something I should have pointed out there, so this is now an orange color on the output. When you take an I and a Q and you do a magnitude squared operation on it, you're taking the square of the I and the Q, and so you end up with just a single number at the output, and so it ends up being a floating point number, just a normal decimal number rather than a complex pair. So we've changed colors there, which means that in the integrate block, we need to change what data type it's expecting. So if I hit OK here, this changes to orange. We want to integrate, just to start out with, by 100, and our vector length again is the FFT size. Something that you can do once you get this running is you can change the amount of integration and see how that affects the end plot. Then we want to do the logarithm option. And the values we're going to use here is we're doing a 10 log 10. So 10 times log 10. I think the documentation, yeah, thankfully has a little bit of useful information here. And I have negative 30 in the flow graph there. It doesn't matter whether we put that in or not. I'll do it for consistency's sake. The reason it doesn't matter again is because we really only care about just putting it onto a log scale in decibels rather than putting it specifically into decibels milliwatt, which is where the negative 30 comes from. And finally, we can view the data. So up above, we were viewing the data with a waterfall sync and a frequency sync. We kind of want to reuse the frequency sync, but we've already done the Fourier transform. So this has that built in. So instead, I have a bug in my version where when I type C, it opens a new flow graph. The block that I've just grabbed is the Qt GUI vector sync, but apparently I can't type vector into there. And so if we do this and update just the vector size one last time, that's the full signal processing connected there. So I know I've kind of just marched all the way through there and there's no checkpoints in there. Does anybody have any questions about the signal processing flow or about how I assembled this together?
What does the virtual source block do? I apologize if you said that and I missed it.
I didn't say it. It is exactly the same thing as if I had done this. So I have a virtual sync here called radio data and then a virtual source. It just cleans it up so the flow graph looks better visually. When you actually generate the Python code from this, this will completely vanish. It has no code attached to it. It's just here for us for convenience sake. I wanted to very clearly distinguish that everything that's happening in the top half here is just reading the data and formatting it. No no meaningful signal processing is being done up here from the perspective of this workshop.
Cool.
So if I got this right and I hit play, and of course that, oh, right, okay. If I hit play, well, that's a really small display there, but we see the same thing that we did before up here, and that's going to slowly go, and then it'll take a little while, but after 100 samples have been processed, we should see, there we are, the data appear here, and it's very badly scaled. So I'll try and zoom in on it a bit better. And sorry, I don't have a way of zooming in on this portion of the screen. We can see right in the center, there's actually an artifact. This is the result of some math errors that have occurred. And so we end up with a little bit of a DC value, and that'll be, if we kind of measured it, we'd find that that's exactly halfway across the spectrum. So this is an artifact.
Is it just me? But I'm just seeing oh, there we go. That's weird. There was just like a white empty space there, and now I'm seeing the spectrum at the top, but no waterfall plot.
Okay, I will quickly, I can never remember, flip to print screen.
Okay, see the spectrum.
Okay.
It might just have been a little delayed because you were sort of talking and pointing at some stuff. There was nothing there.
I've just posted a photo of what I'm currently viewing into Slack for anyone who can't see it. But so this central spike is a DC offset. Basically, there's a small imbalance between the I and the Q values, and math errors have caused that. And because we're looking at such a small signal, it ends up looking very large relative to it. But we have these 3 spikes right off in the corner. And if I zoom in on those, these are actually the carrier and those 2 data sides from Voyager. So compared to doing a long averaging here, and if I actually increase the FFT size a bit, we'll see kind of a closer comparison. We are getting a cleaner image here because we're doing that much finer Fourier transform and the much longer integration than I think the display here is doing. Yeah, I can't really even fool myself into thinking that we can kind of see the spurs off on the side of the averaged one. So yeah, so that is how to do a spectral integration within GNU Radio. Something that's been pointed out to me is that many of the radio astronomy implementations of this don't use a Fourier transform, but instead use something called a polyphase filter bank, which instead of giving you the power levels immediately for a frequency bin, it actually gives you the voltage values for each frequency bin. And that's just some DSP, some digital signal processing that I'm not nearly as familiar with. It's something I'm looking forward to learning more about as we do more stuff with the ATA.
Can you just post again, Derek, what you're seeing now in the zoomed in version? Because I'm still seeing the zoomed out version here, strangely.
Yeah, I can definitely do that. And I hope it's mostly you. Otherwise, everyone's being very quiet about staring at a blank screen.
Not blank, but I'm now seeing what you posted in Slack, but I think you zoomed in on the Voyager signal and we didn't see that.
It must be pretty substantially delayed. Okay. Yes. My computer isn't.
Yeah, I've been seeing the same thing. Just.
Okay.
Yeah. Right.
Sorry for the delay then.
No worries.
So that's all the signal processing that I wanted to do. I can walk through what's done in the top half of the flow graph if people have time and interest. Or of course, if anybody has questions about getting it running locally, we can go over that. But,
and if anyone does need to drop off, and again, we'll have the video of this that I'll circulate later once that's processed. But if folks do need to go, then don't feel like you have to stick around there.
Well, I just want to say thank you, Derek. This is really cool.
Yeah, you're very welcome. Thank you all for your time.
Does anybody have any other questions or want to stick around and work through some of this a bit more?
One quick question. The photo that you posted on Slack, is that, I see three signals there. Is that the two sidebands with the carrier, or is that all the carrier?
It is the two sidebands and the carrier.
Okay.
Yes.
Now we're finally seeing the zoom.
My entire Zoom is my actual Zoom application is totally frozen. So I don't dare try and push any buttons, or I think I'll just vanish. But yeah, so if anybody has questions about getting it running locally, feel free to hit me up in Slack or ask questions now. Otherwise, that's what I have. I guess I'll post a link into Slack rather than trying to show it on my screen, to some more GNU Radio kind of introductory slides, which may explain some of the bits and pieces that I glossed over here. And yeah, I hope that at least for a few people, GNU Radio ends up being something useful for your studies or applications.
Thanks so much, Derek. Really appreciate you taking the time today and in the earlier sessions this summer to lead us through this. I know, this is like doing this as part of my job, but I just do want to emphasize that Derek is really kind of volunteering his time sort of above and beyond the call of duty here to show us all of this cool stuff. So we very much do appreciate it.
Thanks, Derek.
Great, thank you.
Also, Derek, would you be willing to share the slides that you showed us at the beginning?
Yeah, sure. I'll upload a copy of those right now.
Thank you so much.
Okay, thanks everyone. Yeah.
Thank you.